Good morning, everyone, and thank you for joining me today. My name is Andreea Pricopi, and today I'm going to present you the key points of me and my colleagues' work on predicting the geoeffectiveness of coronal mass ejections using machine learning techniques. A more in-depth presentation of our work can be found in the paper that was published in the APJ last year, but hopefully the highlights presented today will inspire you in some way in your work. I will start this presentation by explaining the context of our work, then I'll cover the most successful techniques employed, and finally, I will discuss the challenges that we faced and the approaches that we've used to tackle them. As I was saying, we've applied machine learning techniques to predict the geoeffectiveness of coronal mass ejections, and as some of you may know already, these are powerful solar explosions that can generate geomagnetic storms, meaning they can be geoeffective. And by geoeffective, we understand associated with the DST value lower than or equal to minus 30, DST being a geomagnetic index. The goal of our work was to find an automated way of predicting whether a CME will generate a geomagnetic storm or not, using only solar parameters so as to ensure the longest possible learning time. And as we're going to move on to the actual machine learning techniques employed, what I need you to keep in mind is that their task was to classify a CME as potentially geoeffective or not. The data that we've used consisted of CME attributes from the LASCO catalog plus an additional attribute, the flare index, and these were all correlated with the DST values as per the Richardson and Kane catalog. Before moving on to the methods employed, it is perhaps worth mentioning that we've experimented with multiple algorithms, and these presented here are the ones that have led to the best results. Also, as those of you who are familiar with deep learning techniques have probably noticed already, this is not deep learning. However, I have trust that you will learn a great deal of interesting and complex things from the other presentations today, and my goal is to show you that you can still do great things with otherwise simple methods, and as I was saying, hopefully inspire you in some way. One of the methods that were used for classification was k-nearest neighbors, and I'd like to start with it because of how intuitive it is. I like to think of it as the mathematical way of saying birds of a feather flock together. And this is because the way it predicts the class of an object is by looking at all the objects in our dataset, finding the k most similar ones, looking at what class the majority of them belong to, and then predicting that class as being the right one for the queried object. Similarity here is computed based on the distance between all the features of the models, and obviously the lower the distance or the nearer the objects, the more similar they are, and thus the more likely to belong to the same class. The other method we've successfully used was logistic regression, and yes, this is a statistical method. You might be familiar with it already. You've got the mathematical formula here, but what it basically does is it finds the curve that would best separate the two classes. And as I was saying, these two methods were the ones that led to the best results. And the natural question might be, which one of them was the best one? And well, the answer is both of these methods combined. Combining them creates a so-called ensemble model. And this model basically takes the two individual predictions as inputs and combines them to compute the final prediction. How exactly does it combine them? Well, using an additional model called a meta-learner that in our case is nothing else than another logistic regressor. So we get the solar features that we have, we input them to the KNN classifier and the logistic regressor. We get their individual predictions, and we feed these predictions to a model that has been trained to find the best way to combine them, and then we get a prediction as to whether the CME might be geoeffective or not. Is that it, you might ask? And well, it could have been in a perfect world in which the data is not messy, but our data looked something like this. So the machine has to find a general rule to identify orange dots in an ocean of black ones, if you will. More formally, the geoeffective to non-geoeffective ratio of our examples was roughly 9 to 9 to 1, which leads us to the challenges of these tasks. The most pressing one was, as you have already seen, the extreme imbalance between the two classes. Additionally, we have a very limited number of inputs that we can use, on top of which there's a layer of uncertainty. This is because geomagnetic storms can be caused by other solar phenomena, or we can have even multiple consecutive CMEs, making it hard to distinguish, in some cases, which of them caused this actual storm with absolute certainty. So there is a possibility that the data may be noisy and there's no actual way of knowing what the noise is. And speaking of noise, I'd like you to really get a feel for these complexities of this task, and I like analogies. So to put it in context, please try to imagine that your task is how to play the guitar in 100 hours. But you can only practice playing an actual guitar for 1 hour, and the other 99 you spend practicing playing the violin because that's all you have. And while at the end of those 100 hours you're expected to be able to play anything, you can only practice on 5 songs. And additionally, you might have to play a banjo or a cello, and you'll never know what kind of guitar you'll play. It could be electric, it could be acoustic. You won't know. Thank you for bearing with me through this. I'll get back to the serious stuff now, which is what did we do about these issues? And while we've tried multiple stuff, I unfortunately do not have the time to go through it all. So we'll go through what we've focused on mostly, which is fighting the extreme imbalance. The technique that helped the most, and while perhaps also the most obvious one, I feel like it should really be pointed out as the thing to do when you have imbalanced classes, is to use class weights. Now here comes a little intermezzo on training machine learning models that we will then build upon to understand the role of the class weights. So simplistically, what a model does is it tries to output values y hat that are as close to the true values y as possible, which means finding the parameters of a hypothetical function f that best models the data. And this best is in terms of an error function that's commonly referred to as lost or cost interchangeably, though there is a nuance to each, but let's not get into this. And so the model attempts to make a prediction y hat. It sees how far from the real value y it is, and based on this information, it tweaks its parameters. Then it predicts a new y hat based on new inputs and the now adjusted parameters, and so on until the error is sufficiently low. Now, when we introduce class weights, what we do is we basically say, make bigger changes when you make mistakes while having minority samples as inputs, because you won't see many of those, so try to accommodate for their meaning now. As you see, the weight of a class is actually inversely proportional to the frequency of the class's appearances in the dataset. And as I was trying to say, the error between the predicted y hat and the real y is multiplied with this weight c, and it's resulting in bigger or smaller changes to the model's parameters based on whether the sample that's been predicted on belongs to the minority or the majority class, respectively. The next approach that we've tried was creating artificial geoeffective samples using a technique called SMOTE, or synthetic minority oversampling technique. And in order to understand how this technique works, we'll go back to k nearest neighbors because this is what lies at its basis. So a sample is a point in an n-dimensional space where n is the number of features. In order to generate a new sample, an existing point from the minority class is chosen randomly together with k of the most similar points from the same class, or in other words, it's k nearest neighbors. Out of the k neighbors, one is selected randomly, and then a new point is generated arbitrarily on the line between the original point and the chosen neighbor. Thus, a new sample has been created. Its feature values are the coordinates of the newly generated point. And you can see that the idea is, again, that objects from the same class will be grouped together. But this, together with the randomness, leads to a substantial disadvantage, which is the lack of consideration regarding the positioning of this newly generated point in relation to other existent ones from a different class. So this means that a new point could have the exact same or very similar attributes to a point from a different class, yet still have a different label. Visually, this would mean that this green dot might overlap a black one, or as you can see, it's very close or very similar to black ones, yet its final label will be orange, or geoeffective in our case. Given this and the numerous non-geoeffective samples that we have in our dataset, the changes in performance SMOTE has brought for us were not significant. And so we've employed another technique, which was tweaking the threshold for class separation. Recalling that the model predicts a value y hat, most values predict a y hat value that's between 0 and 1 for this kind of task, and then the actual binary value, 0 or 1, which is not geoeffective or geoeffective respectively, is assigned based on whether y hat is lower than or greater than 0 to 0.5 respectively. And we figured that if we increase this value that the comparison is made based on, the model becomes more confident, so to say, when a CME is actually geoeffective, and in the end it generates less false alarms. Lastly, these are the results on the test set, which means that we correctly identify almost 80% of the geoeffective events and almost 97% of the ones that are not geoeffective. It is important to note here that given the risks of not being ready for a powerful geomagnetic storm, therefore the risks of not identifying a potentially geoeffective CME, identifying as many potential ones as possible is the key metric here, or the recall. Visually, the predictions look like this. For obtaining this 2D visual representation of our data, we have used a technique called UMAP that is really worth checking out. And well, in terms of what these results mean, then again, we consider that in the case of geoeffectiveness predictions, the recall or the proportion of geoeffective events correctly identified is the most important performance indicator because of the high cost associated with the false negative. in the eventuality of a powerful storm. And therefore, we believe that the recall values that we've obtained, meaning our best being approximately 80% for the ensemble classifier, um, prove the utility of our models, given that only solar parameters have been used, which ensures extended warning times. Additionally, one of the most important remarks that emerged from this study is that the majority of the false alarms reported by our models are associated with full halo CMEs, which is in agreement with the current beliefs that full halo CMEs are the ones that are having the highest probability of being geoeffective and also are being associated with the most powerful storms. So the precision values here are justified by this high rate of geomagnetic storm caused by full halo CMEs. And here also comes the fact that halo CMEs are observed equally well as originating both on the front side and the back side of the sun. And while backside CMEs do not reach Earth and thus are not geoeffective, the observations and catalogs, or at least the ones that we've used, do not generally discern between these two classes, which is another complexity factor for this task. And in these circumstances, we consider our results to be promising in spite of the limitations imposed by the nature of the data that we've presented. Compared to the other similar works in the literature, we used a considerably bigger data set. We're not restricting the type of CMEs we used. We're including all geomagnetic storms. We're not limiting the warning time, which is because we're using solar parameters only, and we're not making any type of additional computations while still identifying similar proportions of the geoeffective CMEs. Finally, I hope that this sparked some curiosity, either related to our work or machine learning in general. And in case you want to find out more, as I was saying, there's a paper we've published going through all these aspects and more in more detail. And also, I am open to all of your questions and looking forward to them. This being said, thank you very much for your attention today.